Okay, let's start. Hello and welcome everyone to the next and already last part of the Kubernetes 101 webinar series. My name is Caroline and I'm happy to see that you're joining tonight to learn more about how to keep the state of apps. We already had 2 sessions on this topic before, but since this is a quite complex one, we decided to split this in 3 parts, and this is gonna be the last one tonight. Our speaker for today's webinar is Frank, who works as a solution engineer at Kubermatic and who will be explaining you how statefulsets differ from deployments, how to care for volumes for the pods, and which role a service has in statefulsets. As always, if you have any questions during the presentation, please use the Q&A chat window below so that we either can answer them straight away or in the Q&A session right after the talk. And one second note to make, as always, in case you need to drop out earlier, we are recording the session and we will send out the replay in the coming days. So that's it from my side. I hope you'll enjoy it, have fun, and Frank, now the stage is yours.
Yes, thank you, Karen. Yeah, my name is Frank, as Karen said, and I want to welcome you too. Just one moment. So here's the next slide. That's me. I'm, as Karen said, solution engineer and team lead here in professional services of Kubermatic, and I'm a pretty older guy now than 30 years in business. Mainly this career has been focused on development topics, and also right now in Kubernetes, I like the development of operators. And I had the luck of being author and speaker at different conferences. And so now today I'm going to tell you something about statefulsets. Let's have a look back to what we already know about states in Kubernetes, and what, for example, in the last session I told you. It's that we already know that individual pods can easily be created. They are the atom of scheduling for containers or for groups of containers. Pods of the same type are functionally identically, and so therefore they are ephemeral and replaceable. And they can be used to group multiple containers and shared volumes inside these pods, but they have no real state. Those containers inside the pod or inside one pod are very tightly coupled, so they communicate via local host, or they use the same volume, for example, inside the pod, and they share the IP address, the ports and the namespaces. So that's the most important part about pods. That's good to know, but not what we wanted to know in this webinar. So there's also a possibility to have multiple interchangeable sets of pods. This is called ReplicaSets. They keep pods running by recreating them in case they are deleted or they are have an internal error and have to be restarted. And they maintain the states as far as not real persistent states. And they offer a control of the number of running pods. That's the foundation for scaling. So you can say, I create a small replica set with only 1 or 2 pods inside of it, but also you can set this number higher and say, I want to have this replica sets with 10 pods of the same type. The grouping of the pods inside a replica set is done by label selectors, which are quite flexible with direct values or with group of values and stuff like that. So you will see examples for it. And here, for example, is one schematic one. It's a replica set with 3 replicas. The selector says, I want to match the label demo and to match the expression that the key color and the operator in and the values red and blue. And so if I have 3 pods with these different kind of labels, I put them all together in the replica set, and that's quite flexible, especially for upgrade situations. But also you can imagine if you do it by hand, it's not very simple. So that's also why there are better types in Kubernetes. So one of it is deployment, and the deployment is a reliable mechanism for this whole typical work of creating, updating, and managing of replica sets. They also handle this whole updating and scaling stuff by far more convenient. They provide rollout and rollback functionality and update control. So that's a more daily kind of job, how you work with those kind of pods in a typical scalable modern environment. The technical mechanism behind it is called pod template hash label. This way they are marked internally so that the deployment knows by using internally a replica set how this is put together. And then there are also iterations. So if you do different kind of updates, these iterations create unique labels for the replica set and the subsequent pods of it. And so deployment knows this stuff is one iteration, this is the next iteration, and this way you can do also rollback. And yes, you can directly edit then in place with kube control edit, and with kube control apply, you can apply the manifests. So that's what we know from the past, but here's nothing really to maintain state. So we need more. We want to have 4 modern solutions, especially you will see the use cases in the next slides. We want to have, or we have use cases with stable or where we need stable and unique network identifiers, so that we have a name by which we can address those pods of a group of pods. We want to have stable and persistent storage. So if we have a pod with a given name, how we address it, it shall have its persistent storage, which is always directly assigned of it. We want to have an ordered and graceful deployment and scaling, not a, I say, quite wild one. It should be really ordered, because we have software which needs a kind of order. And we want to have automated rolling updates, because here different software have different requirements, but we have software which requires very ordered and good and automated rolling update. And the same is when we don't need it anymore, it should be deleted and terminated terminated and deleted in a graceful, ordered way. So examples of it are mostly, interestingly, databases. Here, for example, it's a PostgreSQL database where we say we have a service database, which is the entry as the whole service, the database service. And then we have 3 pods, and the first pod is the primary pod, and the 2 other pods are replica pods, for example, and they all have their individual volumes, or even more modern and scalable databases, which are scalable, for example. It's like Cassandra. Cassandra, and in this case, it's configured with 5 nodes, and I want to talk to it as the Cassandra database. So I have the service in front, but then I have the different pods behind it, and they build between each other. They build their typical way of how Cassandra is networked, but to me, it's very interesting that I have all of them together with their volumes in a quite ordered way so that I can address them each time. So the solution here that is currently offered by Kubernetes is that you create a headless service, which is responsible for the network identity of the pods. That's simply the task of it. It's not part of the Statefulset itself, but then you configure your Statefulset where you say everything you need about the pods which are inside of it, the number of the pods, and the volumes you need. And you need a persistent volume provisioner, because you only tell the Statefulset, or inside the Statefulset, that your pods need this and this kind of volume by configuring templates. So you say in your pod template, you're saying this this volume here in this path is addressing the template with the name foo, and the name foo then gets the according storage by the persistent volume provisioner. It will be shown in the next part. So what will be more interesting to you is how to specify such a kind of Statefulset. And there are different parts inside of it beside the typical Kubernetes parts like the name and the top. But inside the spec, there is a selector to match the specific pods. There's a service name, because somehow you have to match the configured service. You define the number of replicas you want to have in the beginning. You always can scale it later, but you have to do some kind of replica number there. A revision history limit, which defines for the rollbacks of the service set that you how many revisions should be stored or kept. Then there are different update strategies. I will show you the template for the pods themselves, so that the pods can be configured by using this template. Also well-known technology here at this time. And the mentioned volumeClaim template, so that the needed volumes for each pod, which is inside the template, is then delivered by the matching volumeClaim template. the example will show it too. So here I've got an example for nginx. It's not a database, but this is a quite simple example using an application which should be scalable and also needs individual volumes. And here in the use case of this example, we simply want to have fixed addresses for them to talk to these different servers. So what we have is what I said, the typical head, the API version, the kind, the metadata, and then the spec. And here is a selector where we say we match the labels app nginx. And this nginx label here has to match inside the same manifest, the spec template metadata labels, as you will see later. Then we provide this here for the service name nginx. This will come in the next part. We start with 3 replicas. If this replica isn't configured, this one would be a replica number of 1. So sounds a bit weird. Why only 1 is a kind of replica, but it's simply the way how the system starts, and yeah, you don't have to set a value. It has, or you can start with 1 and then later scale the system up. And here in the revision history limit also is a numeric entry. In this case, I said we keep 3 revisions of statefulsets, and the default value, if we don't add this value or this parameter here, it's 10. So you typically would have up to 10 iterations of the statefulset, and with the 11th one, the first one would be dropped again. And we have an update strategy, the template, and the volumeClaim templates. So we move to these. The update strategy. It's a quite simple part. It's simply that you have a type in there. In this case, I have the type rolling update, and the rolling update also needs a partition number, and the partition number specifies the ordinal number for the pod updates. I will show what it exactly means later. It is that you have also a second type that is on delete, but yeah, I will show later. The nginx template here is the template for the pod, and here once again you have metadata labels so that you can match, or you have to match the spec selector match labels in the top. So let me quick jump back. This one here, so that this selector and this selector match each other, and then you have the real spec of the pod where you can define your containers. And one point that's really interesting here, that is what I said is the volume mounts, and the volume mounts are based on the volumeClaim templates we have seen here in the bottom. And oops, too quick. So here again, so I have the volume mounts, and I set I want to have a volume, in my case, with the ID www, and it should be mounted under user share nginx HTML. And so now we come to the volumeClaim templates. And this is, yeah, the name is already saying it. It's just a template. It's not that I say, this is the volume. Here I don't define the volume. Here I say, I have a storage class name. Oops. Two quick fingers on the keyboard. I have a storage class name that has to be available in your cluster, depending on where you have installed everything. If it is on let's say, GCP or AWS. This metadata name is the one that is chosen here. And then the volume is provisioned and directly assigned to the new created pod. And here we have only be aware that it is for every pod. So if you of this template. So if you say I in a StatefulSet have a replica set with, let's say, 25 of these nginx containers or pods, then I've got 25 volumes here, as shown in the graphics in the beginning. So that's important. And that's not directly part of the StatefulSet, but needed. We need our headless service for the naming of everything, and the service then has the name nginx here and selects the web or nginx service name we done in the top. Say here. There we matched it, yes. So adding a service. So this whole as a manifest with the two different parts in it produces the service nginx and the pods, the nginx pods, but they don't have the name nginx. Those pods have the names web 0, web 1, web 2. Here you see that they are ordinal and start always by 0. So and if you have now, or if you now scale up, then you have web 3, web 4, web 5. And if you scale down, in the different order, they will scale down. So you will have web 5, 4, 3, 2, and the final one will be web 0. And this is quite interesting for those softwares who need a kind of controlling part, master part in the number 0, especially databases. Here, nginx not so the right part. And as you see, all of them have their individual volumes. So as mentioned in the specification, they are all get their own volume provisioned. So some of the specification fields, which aren't quite interesting, is the revision history limit, as mentioned, but we already know it from deployments. The StatefulSets keep multiple revisions for rollbacks, and this parameter here sets the maximum number of capped revisions. And so once we have more updates than this number here, at the end of the queue, the older revisions will get dropped. And you can easily roll back the stateful sets. And the default limit, if you don't specify, is 10. And the update strategy I already mentioned defines how the updating inside a stateful set happens. One type is on delete, and here the new instance of a pod is directly deployed after the current instance is deleted. So it simply grabs one pod, deletes it, and then starts or deploys a new one. And the rolling update in opposite is updating the pods with an ordinal greater than the value of the partition. So in the example, I had a partition number by 0, but 1 by 1 in reverse order. So what does it mean? Let's jump back again. Where do I have? Here, this one, and we have here our 3. So let's see the graphics. If I here do now with the partition number 0, if I do an update, the number 2 gets dropped, 1 gets dropped, 0 gets dropped, and then 0, 1, 2 gets created again. So it's but I can also say I want to have my number 0 as a static one. Then I would say the partition number should be 1, and then the 2 and 1 would get dropped and updated, but 0 would stay. So, and yeah, that's here. So, and the volumeClaim templates, yes, it's just a template for the request of each volume that is requested by each new pod instance inside the stateful set. And the pod template references the template with the ID and the or the name, and the volume gets then provisioned and assigned. And in case of a rescheduling pod, in case it's killed, the node is killed, or it is deleted, the persistent volume afterwards, when it's restarted, is mounted again. So that's one of the static points of the stateful set. And which also very important for those who are using this, the persistent volumes don't get deleted when pods or stateful sets get deleted. The pods is surely good, but in case you delete a whole stateful set and say, I don't want it anymore, the persistent volumes stay. This has to be done manually. So, one moment from keyword here. Yeah, what do I get? So we have seen the graphics on the service and the 3 nginx pods called Web 0 to Web 2. And on the command line, we can say that we want to get the service nginx just to see it there. And here we get our service nginx with the cluster IP. And yeah, in this example, it's quite young. And if I, a few seconds later, do a kube control get statefulset web, then I get the statefulset. And it has here in this example 3 desired pods. You've seen it. And currently is one already deployed. And yeah, we would now wait for the other ones. And as you can see here, with -w, you have the possibility to get a look into how they get created. And you see Web 0 gets created totally until it's running. And then when it's running, then Web 1 is starting with that it's first pending and then creating and then running. And now after Web 1, the Web 2 would get started. So it's the whole creation is in an ordered way. It's not only that the kickoff is in an ordered way, because even then you can have a race condition. No, it's waiting until everything is running, or the not everything in the ordered way, the one before is running. So then, yeah, the headless service. So if I now see, I can dig by a name. I will show the name scheme later. And if you then see it, you can dig for the name nginx. That is the service name. And then you see that we have, in the end, for example, 3 different addresses here. And if I take a look at only Web 0, then I've got the exactly 1 here, and the 1 here, that is Web 0, which I'm looking at. And this example is the second one of the list before. It's 10.255.02 as address. The pods and the host names are also interesting. Yeah, if you take a look at the pods, then you see again that you have this Web 0, Web 1, Web 2. And interesting is that you can do a kube-control-exec inside of them and retrieve the host names. And you would see you have exactly the same host names, Web 0, Web 1, Web 2. So that the application inside of it can also rely on it. That's very important. Stable storage, that's also what we wanted. That is that if you take a look at the created persistent volume claims, then you have the www, that's the name of the inside the template dash, and then Web 0, that's the name of the pod, so that you see the claim and the name of the pod together build this deployed service. I don't wrong wording. The storage. So, and here's the name pattern. So the service domain names that are created is always the statefulset name and the ordinal. And then the service name, so dot service name, then dot namespace. So in this example, we had default as namespace, and then dot service dot cluster dot local in the end. And also the volumes, as I said, have the volume claim as a beginning, and then the stateful set and the ordinal by dashed, separated by dashed. Yeah, so that's mostly what we want. We want to have reliability. We want to have names on who we can rely, and which are repeatable and not so hash-based names, which are always different when something is restarting. That's already good. And if you want to take a look at the restart behavior, then you can simply try it. If you delete the pods, all the pods get recreated. You can see how they get recreated once again inside, or the recreating is in the correct order again. And what is very interesting is the IP addresses themselves will change, but the DNS host and the host names will stay. So your application, which is relying on this information, can reuse it. And if you do your digging again, you see how these addresses changed, but the names are the same as before. And that's what we want. Yeah, so the benefits, that is that we have the reliability and the scalability like we already know from deployments. Also the convenience and the power regarding the update behavior and the rollback behavior. We have, in addition to it, the ordered behavior in the whole rollout situation. Also later, when we have to done error handling, or when we're scaling down, for example, it's always ordered. And we have stable namings and stable storage assignments, which is also, especially for databases, quite important. Yeah, and already set the revision history for rollbacks, like in deployments. So it's a nice package for databases in every kind. Good. So, any questions?
Well, in the chat, I haven't seen any questions. Maybe someone still has a question. Okay, you don't have to ask them right here, right now. You can either send us an email to marketing@kubermatic.com, or you can directly reach out to Frank to discuss your open topics, to go through your questions with him immediately. And just very short on our own behalf, we are going to host a joint webinar together with Google on January 26th at 5 p.m. Topic will be how to migrate hundreds clusters from on-prem to Google Cloud without downtime. And I'd like to warmly invite you all to join us for this interactive journey. And of course, we are always happy about new followers on Twitter and about GitHub stars for our open source projects. So support is highly appreciated. Thank you very much for joining today. I hope you could learn something from the session and that you enjoyed the whole webinar series. We are happy to receive your feedback if there's anything you think we should improve for the next webinars. Yeah, but for now, I all wish you a very nice evening, Merry Christmas, and a Happy New Year. See you all soon again.
Yeah, from my side too.
Thank you.
Thanks.